Okay, hello and welcome to my channel. Today we're going to be talking about note theorem, a very interesting topic with a bunch of exercise for you to prove these theorem. So the first one is that, well, with psi 1, psi 2, and psi 3, these would be corresponding with, okay, G1 would be corresponding to these three energy. And in note theorem, it is stated that when this happens, E1 would be less than E2, and that would be less than E3. And this one is, all of these note theorem statements are proven in the exercises in a course that I took in like 10th grade, which is 2 years ago. So if you want me to do some videos on me solving those problems for you, please leave a comment so that I know that you guys are interested. Like only one comment is enough and I would do those videos. Okay, so let's get back to our note theorem here. Next statement is that when you have an energy eigenstate psi n, this would have n minus 1 nodes. So this counts as you start the ground state with E1. Yep. Okay, the next one is that your psi and your psi prime, which is the derivative of your psi, cannot be zero simultaneously. And there is one way to prove this rigorously. So it's going to be using a bunch of math and some very weird thing called the Wronskian determinant. But here you just want to imagine something, that when this guy is 0, consequently the probability density would be also 0. So that means that there are no probability. And then the rate of change, or the slope, whatever you want to call it, is also 0. So that means that the probability density is 0 and it is gonna stay 0 through time. Therefore, there are no wave function for us to consider. Therefore, this is unphysical. So it is invalid. That is just a way to know this intuitively. And there is also a way to prove this rigorously, which I'm gonna make a video about if you guys are interested. Next is that, well, bound state of it's of a potential V1 when it goes to infinity, are the bound state of your of another potential V2 that contains V1. So it is kind of hard to, so I will just write the statement down first, and next we're gonna see to, is it A? Yeah, R. So let's take a look right here. Um, this guy is V2, and this guy is P1. This is minus A to A. So your V1 is an infinite square well potential. So V1 of X is V2 inside and infinity outside. Alright, there we go. So this is pretty hard or easy, not that hard, not that easy to understand and visualize. So suppose you have an infinite square well potential, you slap it straight into another potential. This is called screening. So this potential would be your screen potential. Like imagine taking a screen and only seeing one part, like you're doom scrolling on your phone, you can only see like a part of the video compared to you like projecting it on a TV. Yeah, think about it like that. And take your screen potential here and shrink it. When you shrink it enough, you shrink it, and to a point, the bottom here is gonna be flat, meaning that you just get, well, the thing that we dealt with before, something like this, just the infinite square well potential. And now we would want to illustrate the part where it says that bound states of this is also bound states of this. Now, as you know, this guy would have E ground and E1. I would just draw these two, as I'm not that good at plotting these energy eigenstates. So suppose let's take your E ground state first. Now you shrink it to this point and you would get this. And some people might ask, if you expand it again, will this guy gonna, well, sort of change in weird ways? So can this guy, well, when you expand this, find some place here. Suppose when you expand it, it's minus A and A. Suppose you go to like from minus A prime to A prime. Will this go like that? And the answer is no. Well, it is going to be very clear very soon. And I will erase this one. Okay, and you might ask, well, why? When it expands, everything can happen, right? But no, you gotta also consider these three statements. And well, the most important one is this one. The wave function and its derivative cannot be zero simultaneously. And when you stretch it out and get something like this, meaning in between. So get this in between A and A prime, meaning that when you stretch A to A prime, there is an A double prime that is the middle frame of that. So, okay, maybe I should use the E2, I mean E3 if you count from E1. Because it's easier to draw, that's it. It is, well, something like that. And in your A double prime, for you to go from this one, so from this to this, meaning it has to bend down. It's going to change because it's changing. There's going to be a point where it is like this. So imagine this touch, okay? This touches. And here it is 0, 0, 0. And here 0, 0, that's normal. And here, this is the point you want to focus on. This is where your psi is 0 and your derivative of psi is also 0. And that violates this statement already. So yeah, this guy is not allowed. Boom, we're done. That's basically the simple part for note theorem. And as I said like 2 times before, if you're interested in seeing me solving these problems from a course that I took like 2 years ago that would prove these statements more rigorously, I would love to make a video on that. So please comment and let me know. And that's it for today. Goodbye.